Good morning, everyone, and welcome once again to the JKMRC Friday Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the traditional owners and custodians of the land on which we meet today. We pay our respects to the ancestors and their descendants who continue cultural and spiritual connections with country, and we recognize their valuable contributions to Australia and the global society. It's my great pleasure today to welcome Mr. Dave Sammut. Dave has degrees in both science and business and has worked for 30 years in active industrial R&D, commercialization, entrepreneurship, and in professional communication to government and investor relations and audiences. He's recognized as a global expert in chloride hydrometallurgy. That's what he's going to talk to us today about, with over 60 published papers and articles, and is the inventor of the breakthrough Halion trademark technology for the clean production of copper and other metals. Today, as stated, Dave will talk to us about the Halion trademark technology, copper made green. Why don't you join me? Welcome, Dave.
Okay, better? Better, okay. We good? Okay. By 2050, to achieve global emission targets, we are going to need to mine more copper in the next 25 years than in all of human history to date. And that is one heck of a challenge. Demand is only accelerating, particularly the demand in the clean tech sector. Demand increases at the moment by approximately 500,000 tonnes per annum of new copper requirement, of which approximately 300,000 tonnes per annum is attributable to the growth in the green copper market. Am I good to progress? Okay, great. So that demand is growing significantly, as I say, particularly in the renewable sector. There are actually projects that I'm hearing about now, such as a wind farm off England, that is literally having trouble supplying sufficient copper, and it's causing project delays. So we're already starting to see this supply shortfall starting to bite. So as I say, 25%, 8 million tonnes per annum shortfall by 2030. No, that's all right. I was about to move on anyway, so we're good. Okay. And on the supply side, we've got the fundamental problem that smelting, which is literally Bronze Age technology, simply cannot cope, right? Over the last 20 years, the average head grade of copper ores has dropped by 50%. We are increasingly facing the challenge that we are running out, or it has been over 10 years since a major new copper resource discovery has been made, and we are simply running out of clean, high-grade copper resources in politically stable jurisdictions. I'll keep talking. The world urgently needs clean, versatile new technologies that can process the low-grade, the polymetallic, and the arsenic-contaminated resources that we actually have available to us in those politically stable jurisdictions. Alrighty, here we go. And just flick me to the next if I can. There we go. So smelting still represents 80% of world's copper supply. Pressure oxidation or hydrometallurgy has made slow but very slow progress. When you consider that it's been sort of 25 years of emerging hydromet technologies, its slow penetration into the market has been surprising, I think, across the board. And I think it shows the limitations of the existing major technologies that I will be talking about. Um, the remaining 20% of the world's copper production is primarily pressure oxidation, such as Odotech. It's heap leaching, and it is bacterial oxidation. There's pretty much only 3 versions of hydromet that are commercial out there, although I will note that there are more than 50 suggested technologies out there that simply haven't made it to market. It's a difficult area to get into. For those of you who aren't already familiar, smelting typically requires 2 major furnace steps and a refinery. So you're typically talking 5,000 kilometres of transport, major energy inputs, and pretty significant carbon impacts. But what's interesting about this is that, of course, if you're only analysing carbon, then smelting gets a great big cheat, because most of its energy comes by burning sulfur to make acid rain, which isn't a carbon problem, but is still a problem. I mean, historically, the smelter at Mount Isa, which is this photo here, had a 100-kilometre stretch of dead trees in the direction of the prevailing winds. Okay. And then, of course, you've got all of the smelt penalties. So when you take your concentrate, and 57% of Australia's copper is produced in concentrate and exported to China. Over half of our product is exported as concentrate, and that's a big loss to our country. You've got your transport costs, you've got your TCR, your treatment charges and refining charges, you've got your payable metal discounts, and you've got your penalty elements, all of which are dragging down on the bottom line for your Australian miners. These are some examples of the penalties. What I find fascinating is that you can be selling a copper concentrate and it doesn't have to have much zinc in it before you start paying a penalty for a valuable and useful element. This is an area where we can achieve a pretty significant uplift. And if we look at pressure oxidation, such as the Albion process, but many other processes, obviously it works well in the sense that you can extract your metals into solution over about 8 hours. But in doing it, and you can do that in a sulfate environment, but pressure oxidation is expensive, high capital cost, and it also has a significant carbon footprint. I'll be talking about comparative carbon footprints in a bit, but in short, as a spoiler, the Halion Loop, based on CSIRO modelling, has about 1/3 the carbon footprint of pressure oxidation. But the basic reactions of, now let's see, am I going to get it right? Here we go. The basic reactions of pressure oxidation and the Halion Loop are actually very, very similar. When you're comparing the two technologies, basically we are doing in a chloride environment at atmospheric pressure what pressure oxidation does in a sulfate environment under heavy temperature and pressure. So it's the oxidation of the mineral to form hematite, and I don't actually have an equation for it up there, but it's also the stabilization of arsenic. Pressure oxidation is the one competing technology that's good at dealing with arsenic. Let's give it props, right? Bacterial oxidation is you then start moving up to residence times of 48 to 72 hours, 2 to 3 days. So you're talking significantly larger capital costs for the size of the leach train. And I know I'm biased here, I know I'm an inorganic chemist, but my fundamental criticism of bacterial oxidation is bugs die. You get an interruption to your process, you lose power to your process, your bugs die off, and you're going to spend a month re-inoculating and getting back into operation. You know, in our system, we lose power, we turn the power back on, and 6 hours later you're back up and going. So it's just a lot more robust. I don't think bacterial is a good choice for a lot of areas where power supply is anything less than completely stable. In terms of comparative scale, these days you pretty much would not build a smelter at less than 250,000 tonnes per annum of copper output. You pretty much wouldn't build a pressure oxidation facility smaller than 100,000 tonnes per annum, and probably 150. Your minimum for a for a bacterial is 30 to 50,000 tonnes per annum. And when you get down to the Halion Loop, we don't actually know how small we can go and still be economic. We've modelled it down to 3,000 tonnes per annum and still doing well. So it gives us a lot more flexibility. And that's a key aspect of what I'm going to be talking about with the Halion Loop is we're talking about producing high purity metal directly at the mine site for less than the cost of producing a smelter grade concentrate. We're doing it with zero noxious gas emissions, zero liquid effluents, and the lowest carbon footprint of any of the available technologies. Okay, and of course, then you've got heap leaching. Now, heap leaching is a perfectly sound option for incredibly low value, low concentration ores. But you know, you're going to be waiting 200 to 300 days to get 60, maximum 65% recovery. So it's not at all efficient. And of course, by the way, increasingly these heap leaching operations are facing a really interesting challenge. They work off sulfate chemistry, but if the site is saline, you go from having 4 or 5 sulfate species to deal with, an iron sulfate, a copper sulfate, maybe a zinc and lead sulfate, well, not a lead sulfate, obviously, zinc sulfate or whatever. The second you introduce chloride, now you're going to be dealing with 20 plus chloride species because the chloride chemistry will dominate. You'll have an unholy mess of different redox chemistries, of different pH, precipitation points. Your heap is going to become a big old mess. So then we get into halide leaching. Now, what I love about halide leaching is that it is elegant chemistry. We are basically putting a tiny finger on the scales of nature and letting nature do the work for us. And if you compare that to virtually any other industrial process, in most industrial processes are brute force, high pressure, high temperature, massive energy additions, massive reagent additions, you know, chemical, physical, whatever energy you're putting into it to make the materials do what you want to do. In chloride hydromet, you're basically setting up nature to do what it wants to do anyway. So our basic leach reaction is copper sulfide reacting with cupric to make cuprous ions and ferric ions and elemental sulfur. Now, the formation of elemental sulfur is important because that means that for every molecule of mineral that you're leaching, you're only needing to oxidize 2 electrons of sulfur rather than 8 electrons of sulfur, and therefore your oxidant addition is a great deal less. And in turn, that means that when we reoxidize the cuprous ions with oxygen, we're doing it with air, not with pure oxygen. So in a side-by-side comparison to the Albion process, as example, we did an apples for apples comparison on a published site. Our whole plant costs less than their oxygen plant. And we regenerate cupric. The iron hydrolyzes with water to form hematite. And when you add those 3 reactions together, effectively what you have is the copper catalyzed reaction between mineral and air. So your primary reagent in your process is plain old air. The only thing that's coming out of your process is spent air. So, you know, using about 5% of the oxygen that's present. For a typical mineral, we'll be looking at greater than 99% extraction of all of our major base metals. We'll be looking at 95% of our gold and our PGMs, except for platinum, which often gives us a little bit of trouble. But it's important to recognize that this is direct recovery of those gold and PGMs from the process. It's not cyanidation. So you don't face all of the additional costs of cyanide ponds and all of the hazards and the regulatory hassles that are associated with that as well. Depending on the material that we're dealing with, you can capture a significant portion of the periodic table. So your rare earths, uranium, thorium, certainly your nickel, cobalt, zinc, lead. And what I'll be talking about at some point in this presentation is the polymetallic applications of this. As I said, we operate at atmospheric pressure at less than 100 degrees C, so it's very mild conditions. You could literally, not that I would, but you could literally go and take a swim in our pregnant leach solution. I wouldn't advise it, but the point is you can do it. The only thing that you can't do with our pregnant solution is touch it to anything ferrous. We used to joke that marine grade stainless steel that's made to deal with salt water, which is called marine grade 316 stainless steel, was named 316 because it would last 316 seconds in our process. In a pilot plant that we did a few years ago, we specified, of course, no wetted ferrous parts. A supplier missupplied a peristaltic pump with an inch thick stainless steel flange, and it lasted approximately 9 hours. Primary reagent is air, environmentally stable residues. We're producing hematite, elemental sulfur. If there's arsenic present, we're producing scorodite, which is nice and stable. No noxious gas emissions, no liquid effluents. The elemental sulfur is recoverable if you have a use for it. So the economics of elemental sulfur give you transport of about 100, maybe 150 kilometers. After that, it becomes undesirable, uneconomic. But there are certainly areas. So let's say when the Mount Isa smelter falls over in the next few years, and we go and replace that and start doing treatment for the various copper mines in the Cloncurry district, well, we could extract and recover our sulfur, make it into acid, and sell it back to the miners. We can cover pretty much all of the, you name me a copper mineral, I'll give it back to you, right from your standard eucarbolytes, chalcosites. It's interesting that the industry benchmark for hydrometallurgy is to call chalcopyrite refractory. And I don't consider that remotely refractory. If you give me chalcopyrite, I will give you 99% plus of the copper that's in it. For us, refractory is enegite and tenantite. As well as your lead minerals, your zinc minerals, your nickel minerals. Interestingly, we've developed a new enhanced leaching apparatus that extends the capabilities of our leaching so that we can now actually directly leach pyrite if we want to, which has always been the limiting point of chloride hydrometallurgy. That's always been the one that was unleachable. So that's an interesting addition to our capabilities. I think the key aspect is that we don't need a smelter grade concentrate. We have done successful test work down to concentrates at 7.4% copper and 8% copper. We've done successful leaching of concentrates at 1,080 microns, 1 millimeter. Now, you compare that to existing hydromet technologies, and 25 micron is your standard or smaller. Albion requires 6 microns. The amount of money that you can save at the mill, the amount of water and energy that you can save at the mill will vastly outweigh the costs and inputs of processing using our technology. And again, that's how I come back to saying, by changing your operations at the mill, by directly processing a rougher con instead of running the cleaner circuit, you can save more money at the mill than our cost of production so that you can produce metal at site for less than the cost of producing a smelter grade con. For a typical Australian mine, we're talking C3 mine to metal cash costs of 30 to 40%, which are pretty significant. I'll give you an example. We made our breakthrough that I'm going to be talking about as part of a Think and Act Differently challenge for as was Oz Minerals, but is now BHP, what's called the Think and Act Differently program. I would recommend that program to any researcher who has a great idea. It's a fabulous program to be a part of. As part of that program, they engaged an independent consultant to investigate the cost of processing a conventional 43% copper concentrate. I say conventional, a very high grade 43% copper concentrate from Carrapateena. That independent model came back at 17.6 US cents per pound to process the concentrate. We then went back to BHP and said, but what if we skip the cleaner circuit? And the estimate was that we could save approximately 25 cents per pound by not running the cleaner circuit, and that our cost of production would basically not change. You know, maybe go from 17.6 to 18, but you know, nothing fancy. Now, the published data for Carrapateena says that it cost them 30 cents to mine the metal. It cost them $1 to mill it and produce a float, mill it and float it and produce a con. it costs them 50 cents to transport it to a smelter, TCRCs, payable metal discounts, and penalty elements. So $1.80 is the standard current cost of mine to metal for the Carrapateena site. By processing a rougher con directly at the site, by avoiding all of the costs of transport, TCRCs, etc., we would save that site 58 cents per pound of copper. Multiply that by 2206 pounds per tonne for 73,000 tonnes per annum. That's 95 million US dollars per annum that site could save before byproduct credits. Again, payback period of roughly 2 years on that. I say again, that's the first time I'm saying that. I say it so often that I forget. So what's our big breakthrough? Or actually, just before I talk about that, the concept of hydrometallurgy, of chloride hydrometallurgy, has been thoroughly examined, thoroughly proven. Multiple companies, Metso Outotec, BHP, Nippon Mining and Metals, multiple companies between them have spent nearly $500 million in the 80s, 90s and noughties proving the advantages, the economic and environmental advantages of extracting metals into a chloride solution. The problem was that none of them were able to find a suitable, practical, economic approach to recover the metals back from solution. And without that, you didn't have a closed loop. Most of them went down the track of SX and SXEW, and it was a failure. In short, there are three major reasons why SXEW can't and shouldn't work. The first is simply chloride. If you're starting from a solution that is 6 molar chloride, or halides, let's just say halides, then SX simply cannot give you sufficient selectivity to avoid trace contamination of chloride in your sulfate, which completely buggers up your sulfate electrowinning. Secondly, even if you were successful in performing an SX into a sulfate media, then you immediately lose the major advantage of being in a chloride, and that is we recover our copper directly from the 1+ state. In sulfate, you don't have a 1+ state, so you're back to 2+, and that means you need twice the number of electrons per atom of copper for every atom of copper that you're going to produce. And thirdly, electrowinning is limited, sulfate electrowinning is limited to 375 amps per square meter before you stop getting flat plate cathode. Our new cell that we have developed and I'm going to talk about, we believe it will operate up to 2000 amps per square meter. So we can produce high purity dendrite directly with approximately 20% of the tank house footprint. Okay, so in simple terms, the Halion electrowinning cell operates off some pretty simple chemistry. Whoops, sorry, pardon me, wrong button. You've got your copper 1 reacting with electron to form copper metal. Nice and simple. So we feed catholite feed pregnant liquor into the cathode at catholite at about 80 gram per liter. We do a 50 gram per liter strip. So we produce approximately 50 grams per liter of metal. The catholite then passes through a membrane into an anode chamber where the remaining copper is reoxidized, but critically, because we have the presence of both chloride and bromide, we actually form an aqueous species, Cl2Br-. This is a major advantage because any other chloride-based technology that's done electrowinning, and there have been ones in nickel and silver and things like this, they all produce hot, wet, corrosive chlorine gas in large volumes. It's a materials handling nightmare and a safety nightmare. By keeping your anodic energy in the aqueous phase, you can simply transport that analyte back to your leach and use that power for the leaching of gold and PGMs and things like that. I do have a flow sheet coming up. Okay, so as I say, this material has previously been called Halex, and for now I'm sticking with the name just because it's a name that some people will recognize if we've been around the traps for long enough. But it is certainly capable of directly leaching your gold, your PGMs, etc. And therefore you have a non-cyanide leach. Okay, now is this going to work? Excellent. Our product, We call it coarse copper sand. And I do have a snow globe here for you to play with. For the longest time, the production of dendrite has been considered a major disadvantage of chloride chemistry. One other technology prior to us was called the Intec process. Intec was an Australian company that spent approximately $70 million developing technology in this field. They did develop an electrowinning cell that unfortunately had a number of potential points of failure. So if you could afford to have a person stand there and watch it 24 hours a day, 7 days a week and fix every problem as it occurred, you could have built it. But of course, that's not commercially viable. So it never got to market. The key problem that every researcher in the chloride space has faced is how do you control the growth of dendrites? How do you handle the dendrites that are formed? Now, Intec had this wildly complicated design with these articulated wiping mechanisms that would rise up. They'd go to the top of the cathode, and then they would wipe down and wipe all the dendrites off the cell. And Jenny, who's in the room today, will remember just how nightmarish that process was. It had major disadvantages, particularly that by wiping the entire cathode surface in a single wipe, you massively changed the electrical conditions in the cell. You went from having, okay, a notional surface area of X amount of square meters, but with all that dendrite, your effective surface area was probably 2 to 3 orders of magnitude higher. So when you wiped the cathode, effectively your current density jumped by your effective current density jumped by 2 to 3 orders of magnitude. Your voltage jumped. Your morphology of your product that you produced in the minutes afterwards went to hell, and so did your product purity because of the boundary layers around the much lower surface area. By doing it, and by the way, I grew these dendrites long just to show what an ugly dendrite looks like. So what we've done in the Halion cell is we have deliberately changed the way that we operate the cell to continuously remove a small rain of small particles off the cell. And it's all based on the fact that we figured out how to control the growth of dendrite on a cathode. And then once you figured out how to do that, you can then design your whole cell around an easily operated cathode. So when I say that we can operate at a notional current density of 2000 amp per square meter, by keeping a constant presence of copper dendrite on our cathode, we're keeping a much higher effective surface area. I'd love an academic to tell me how I would measure an effective current density in this environment, but the short version is we are estimating that our actual effective current density would be sub 25 amps per square meter, even if we're notionally putting in 2000 amp per square meter of current. In making small particle dendrites, it then makes the physical handling of the resulting material much easier. The disadvantage is, of course, that high surface area material will now reoxidize quickly. So once you have produced it, you're going to have to then either mush it, there's a good technical term, isn't it? Press it into rondelles or to melt it, from which point you have multiple options. You can, of course, make a cathode or an ingot shape that are commonly traded on the market. But if you're close enough to the right markets, if you've already melted it, why wouldn't you just take it straight through to rod, wire, and pipe? And that's an option that is available to us. I will say that when we do our economic modeling, we just assume that we're producing ingot at a discount, not high-grade materials at an advantage. So, comparing the two types of cell, as I said, in a sulfate cell, we've lost the advantage of the single electron. We believe that, immediately by having a single electron, you straight away halve your power requirement. Because of some other voltage requirements, we believe that our cell will operate at up to 20% power reduction compared to a conventional cell. We'll have a reduction of 80% in our tank house footprint. And most importantly, or just as importantly, where a conventional cell, you have to pull every flat plate of copper product out every 2 to 3 days and manually strip that cathode. Instead, we believe that we will be able to produce copper 24 hours a day, 7 days a week for up to 12 months, without ever touching the cell. We're actually considering as an option the possibility of providing our cells to the users as a black box and simply taking it and maintaining it ourselves once a year. Pardon me. So here's our basic flow sheet. Pardon me. Concentrate is fed into a 3-stage countercurrent leach. I'm going to start with stage 2. Stage 2 is where the guts of your leaching occurs. By the way, everyone taking photos, you are most welcome. Well, I'm going to give you a copy of this presentation. You're most welcome to have the presentation, but go nuts with your photos as well. Leach stage 2 is where the guts of the reaction happen. You are feeding, you've got your mineral reacting with cupric to form cuprous. You've got your cuprous reacting with air to reform cupric, and it just churns through the mineral. We go in a countercurrent, so we've got a thickener, and the clear overflow passes up to leach stage 1, where it's exactly the same reaction, but without the addition of air. So effectively what happens is the freshest mineral reacts with cupric and pushes, by Le Chatelier's principle, pushes the copper into about 97.5%, 98% copper 1. We then run it with a little bit of copper recycle to 100% cuprous. Now, the advantage is that cuprous is pH very stable, whereas a lot of other metals are not. So then all you need to do is raise the pH a little bit, and most of your contaminant metals simply drop out. That's an opportunity to also capture other metals, lead, cobalt, uranium, other things as byproducts, if that's desirable for your project. Then you need to remove the silver. We do it by IX. Silver is actually the most difficult metal to deal with in this process because the chemistry of silver 1 is very, very, very similar to the chemistry of copper 1. And so that's the most difficult chemistry in the process. But you end up with a clear 80 gram per litre copper 1 solution. You feed it to the catholyte, as I said. We do a 50 gram per litre strip to produce copper product. We then take the analyte. Now we may take depending on the project and depending on what contaminant metals are present in the project, you may take a bleed treatment to pull out things like zinc or magnesium or manganese or nickel. And then you take your analyte, you feed it back to leach stage 3. By this stage, the mineral processing down the process is mostly depleted, and so you are putting the highest anodic energy, the highest redox potential against the most depleted mineral, where you extract the last vestiges of the base metals, you extract the lead, the gold, the PGMs, the rare earths, etc. And you take the overflow from the thickener and you IX it to recover those metals. It's a nice closed loop, and you can see why until you had this critical stage, you didn't have a closed loop, and that's why the existing previous technologies didn't get to market. Oh, sorry, just quickly. You can see that I've marked everything by TRL. So most of these steps have been proven. You know, Intech alone ran 10 years of pilot and demonstration plants. And when they got killed off by the GFC in 2012, I was the third last person out the door. They gifted me the 6 gigabyte database of engineering data and said, here, wear out. If you can make something of it, go nuts. So I did exactly that. In terms of the periodic table, we can capture actually a significant portion of the periodic table. I was actually joking with a couple of researchers before that I love being an inorganic chemist. I love being a metallurgist. You know, the poor old organic chemists, they deal with the same 6 elements over and over again for the course of their careers. We get to deal with the entire periodic table. They keep inventing new elements for us to deal with. It's awesome. So we deal with all the base metals, the precious metals, etc. We know that there's partially developed work for a lot of these others that are marked in green, and then the ones in blue, they're all possibilities in one form or another. I'm getting a lot of inquiry about gallium, germanium, tin and antimony at the moment, and we've actually got a really interesting project happening right now on the extraction of stibnite. For which I can't give you a good answer right now. I think the most difficult ones of the possibilities list are going to be vanadium and molybdenum. Those 5 valent states, I think they're going to be a pain in the butt. See, one of the beauties of our process is most of our metals have 1 or 2 valent states. You can easily Just push them in one direction or the other, or a slight pH, a little bit up, a little bit down, and you could make them do what you want to do with just, as I say, that little finger on the scales. Once you get to 5 valent states, I think it'll get tricky. Metal recovery, conventional ion exchange. We've done work with CSIRO and shown conventional IX recovery of your gold and your PGMs. We've done work on silver. It's all coming along. So if I go back to that, you can see that I've marked those IX steps as not being TRL7 yet. But let's face it, IX is thoroughly established technology these days. It's simply a matter of picking the right resin. And we're just talking about using commercial resins. Interesting work that we've done in the last little while. How am I doing for time? Good for time. Okay. We have done, oh, that was an interesting one. So we did a rougher concentrate. You know, it's actually fascinating. I was 30 years in this industry before it ever, and I don't want to say it didn't occur to me. Somebody just said to me, "I've got this." I called an alliance partner. So we work with Brisbane Metallurgical Lab here in Brisbane, and I called my mate Chris Bucknell at Brisbane, and I said, "Have you got any interesting samples? I just, I've got a gap in my lab. I've got some interns that need something to work on. Have you got an interesting sample?" And he sent me the most wonderful sample, which was actually this one. It was 8% copper ore at 1,080 microns, and I can't believe that in 30 years, it had never occurred to me to test a really coarse material. We were all so used to the concept that a concentrate is 25 microns and that's what you get, that it never occurred to me to test something coarse. And of course, that one was a revelation, because in a chloride environment, you don't form a passivation layer on the particle, which is a key limiting factor for sulfate. So in chloride, you just keep eating through the particle until it's gone, and then you reform hematite. So our starting material was 1,080. Our final material from a batch test was 19 microns. And that was just the regrown hematite. If we were doing that industrially, our hematite would be 100 microns. And 99.5% extraction, which was awesome. But going back to the Rufficon, yeah, just one day we said, look, why don't we try it, see what happens? And what was really interesting, not only did we get the copper, but with zero, this was just a scouter study. We didn't, we don't have time and budget to do full optimization. Just a scouter study, we got 70% of the uranium and 70% of the rare earths, just from a simple Rufficon with no optimization. It shows that there's a real opportunity. Now, if we talk briefly about rare earths, there are 4 major minerals that host rare earths. I could be teaching you to suck eggs here. There is bastnasite and apatite, which are basically alkalis, easily acid soluble. Then you've got the darn difficult ones. You've got monazite and xenotime, and they are rare earth phosphates, which are they are just about as difficult to leach as anything I've ever encountered. The existing processes for breaking down monazite, either you mix it with 50% sulfuric acid and you roast it for 24 hours. Okay, sorry, I'll keep it brief. Or you mix it with 50% alkali and you boil it for 48 hours, both of which are expensive and dangerous. We are achieving 70% extraction at atmospheric pressure in less than 100 degrees C. So we're looking at CapEx and OpEx, probably 10% or less of the existing processes. It's an interesting open avenue for investigation. Okay, I've talked about the comparison to existing techs. And I wanted to briefly finish, since there's students in the room, with a couple of quick observations on careers, if I may. I have run a national mentoring program for a dozen years for STEM students, and I love to talk about what's great about careers. I love to say, look, you've picked the perfect industry, an industry with highs and lows, lots of international flights, lots of deep pits. It's a great industry to be in. Okay, secondly, the power of yes. Yes is the most important word in any scientist's lexicon. When you are given any opportunity in the work, I went, in the first 3 years of my career, I went from bucketing mud from place to place in a pilot plant to running a team of people in the research program of what became an ASX listed company, on the simple premise of in a small company, every time I saw something that wasn't being done, put my hand up and said, can I have a go? Just saying yes. is an awesome thing. But most importantly, it's also this. As scientists, we know that an idea progresses from a concept to a hypothesis to a theory to a law by the continual failure to disprove that idea. So naturally, as scientists, when we're presented with a new idea, our first instinct is to hold it up to the light and say, does it work? What's the problems? It's an incredibly destructive thing in the workplace. In the workplace, your first reaction should be yes. Yes, that's interesting. Yes, let's look at it. The more you say yes in the workplace, the faster and better your career will progress. When you're applying for a job, treat the job application as a job. The best predictor of your future behavior is your past behavior. If you want someone, there's no point in saying, if you employ me, I will work hard. Work hard, and then they will employ you. A fair and equal workforce is the most important thing in the world. So I say to every woman, every female student in the room, there is a special spot out there for you in industry. Do not wait for the men around you to offer. Go out there, take those opportunities, demand those opportunities, take a great big bite out of your career, and then chew hard. A versatile career. I think that we live in a delightful world where you don't pick up one job at the beginning of your career and do it for the rest of your life. Embrace flexibility. We are scientists. We are here for the concept of new ideas. Treat your career the same way. Lots of new ideas, lots of new opportunities. And lastly, for anyone who is interested, on YouTube, there is a channel called the Raki Careers Development Program. There are more than 50 careers videos of advice that can further your career. And there we go. I'll finish by saying this. The vision for Loop Hydrometallurgy. Clean copper for clean technology. Millions of tons of transport saved, gigawatts of power, kilotons of carbon, and a new industry cost curve for what we like to call copper made green. Thank you very much, everybody.
Any questions?
I think you mentioned it, but
So basically the point is...
oh no, what's the percentage?
Oh, the percentage?
Yeah.
Typically less than 5%.
Okay.
Interestingly, I've got a really interesting project on my horizon, which is a material that contains native copper. And that native copper could supplant that. That entire step would be unnecessary. So when the native copper is actually a pain in the butt for the miner, it will be a major advantage to us.
And I know you were sort of talking around the electrowinning and the recovery of the dendritic copper. Is it a continuous process?
Yeah. Yeah, so there's a couple of different options on how you can do it, but I think the best option is to follow the same pattern that Sumitomo used back in the early noughties, which was just a high flow slurry. Just push it out, and then the advantage of the flow is also that it will create what's what I'm looking for?
Eddies?
Mixing patterns in your cell, which will help. You know, all the mixing in your cell is useful.
Okay. All right.
Thank you very much, Dave. Excellent talk.
Thank you.
Fascinating. You touched on the corrosive nature of where you're working. And the question is, what does your plant look like? What are your materials of construction?
Very good question.
And how would that affect, in the end, would it be more expensive?
No, we actually use very inexpensive materials. When I say corrosive, of course, everybody's going to think acid, but it's not the acid that's corrosive. It's the galvanic couple between copper and iron. So as long as you're not using anything ferrous, you're completely fine. The primary materials of construction are fiberglass, HDPE, or some of those, nice cheap polymers. Occasionally you use something like PVDF, and very, very occasionally you use titanium.
What about the electrodes?
The electrodes are titanium, simple, off-the-shelf titanium, nothing special.
That was fantastic, Dave. Quick, just most of your test work's been, looks like it's done on various flotation products like that have come out of or what you're presenting here, and it's sort of part of just the conventional production of a material to go to a smelter. If you could design a feedstock that was
specifically designed for this process, would it look like that? I mean, is there another
No,
process that you could generate something more cheaply that would work just as well?
So my favorite is every polymetallic mine in the world, right? Instead of producing 3 separate concentrates, go back to the mill, maximize mill efficiency, maximize metal recovery at the mill. Don't worry about grade. Don't worry about polymetallic. Don't worry about arsenic. Just give me whatever the mill produces that is most efficient from the mill. Because when you leach in chloride, you're smashing a walnut with a sledgehammer. Everything comes into solution, and then you just separate it once it's in solution. So yeah, I'm really looking for the low grade, the polymetallic, the arsenic contaminated. Let's talk about, may I? The example of the Avebury mine in Tasmania. Do you guys know Avebury? It's a nickel mine. In the last 15 years, 3 times they've tried to fire it up. 3 times it has fallen over within 12 months of operation, and it's because of arsenic. They make their mining more expensive by mining around the arsenic. They blend ores, which cost money for no value. They run the mill to minimize arsenic contamination of the product. And still a significant percentage of their concentrate product is unsaleable due to the high arsenic levels. Now, if that was my asset, what I would do is I'd mine for mine efficiency, for low mining cost and mine efficiency. I wouldn't bother with all those stockpile blending. I'd go to the mill and I would mill for nickel recovery. Don't worry about arsenic, don't worry about grade. I would mill for nickel recovery. And then I would take that material, I would extract the nickel, stabilize the arsenic, and just produce an MHP. Don't even worry about nickel metal. Just produce, you could build that with this knowledge today.
We've got 2 questions online. One asked, have you tried this on oxide carbonate minerals?
Yeah, so anything that is oxide or carbonate is acid consuming. Anything that is sulfide is mildly acid producing, or you can run our enhanced leach apparatus and generate acid in situ. So your ideal is to mix a little bit of both and then not need any reagents either way, neither alkaline nor acid.
There's a second one which asked if you've tried this on titanium ores.
No, titanium is not suitable for this technology, simply. Yeah.
Two quick questions. One is, what's the impact on tailings in terms of what's produced? And the second one is in terms of getting this into market and adoption. Are big mining companies willing to invest in technology?
2 very good questions. Okay, firstly, tailings. We obviously have the advantage that the residues coming out of our process are stable. So back in 1999, we got what was called a special immobilization approval under the Protection of the Environment Operations Act in New South Wales that recognised the stability of our material so that you could actually throw it to a standard municipal dump in metropolitan Sydney. So that material is nice and stable. That's an advantage for tailings. Now, if you're talking about reprocessing tailings, I think the economics of reprocessing tailings are difficult because they're very low grade. But what if you can use existing methods to beneficiate it part of the way, get it to 5% copper or 6% copper, and then process it from there? I think there are tailings reprocessing opportunities in that respect. As for who's taking up the technology, well, I think there are grey heads in the room, much like mine, that would tell you that the mining industry rushes to be second. Getting anyone to be the first. I mean, the first question I get from every single miner is, where is this in operation? And the answer is not yet. But once we get that one, so I talked about Avebury for a moment ago. That's an example of a principle where we will do what we call a track 1 project. We'll get a plant in operation that doesn't require the cell yet, add to the cell to it later, develop it in 2 stages. But once you have that reference facility, a place that the world can touch, taste, feel, smell, you'll fire a rocket under your take-up.
obviously a lot of the sulfuric acid production, for example.
Yeah. Yeah. Nope. So in our standard model, we use tiny amounts of sulfuric acid and tiny amounts of limestone. You do it right, you don't need either. Our primary reagent is air. Now, interestingly, during our electrowinning, we don't use any additives. So in terms of reagents, it's going to be air and your IX resins. That's pretty much it. I mean, we do use a small amount of sodium bromide and sodium chloride, mostly during first fill, but then on ongoing, the amount of salt that you lose is entirely and directly related to how well you wash your residues. Because you wash your residues, you put your salts back into the process.
I had a great talk. Really enjoyed it. It's a very exciting area. I was at the World Copper thing earlier on this year in Santiago, and somehow, without me noticing, this has become one of the things that seems to be most on people's mind in the copper space, the whole, hydromet recovery of copper. So it seems like a really timely thing to be working on. And my question was, and the other thing I wanted to say was that my dad was an organic chemist. And so I have to say that he may have only had 6 elements, but I remember a coffee table, a long coffee table being absolutely covered with these complex 3D, this was before computer models, so big complex 3D models of molecules that he would have his students come and they'd be playing with them in our living room. But anyway, my question comes back to your point about the very frustrating thing that lots and lots of people point out where you say, I've got this fantastic technology and the mining company says, that's great, show me where it's absolutely working, 100% de-risked, and we can adopt it without any problem whatsoever. And I know that that's a huge problem. And some of the companies at that World Copper Conference, like FLS and others, are now incorporating ways to circumvent that into their technology development, like saying, okay, what is our specific strategy to get this implemented somewhere, to share costs or to subsidize it or whatever, to get over that hurdle that can, take years or decades to get through. So what's your strategy to get over that hurdle? Because hope's not a strategy.
No, I agree. There's multiple avenues to overcoming that reticence. The first is, of course, that there are projects that we can develop using the existing knowledge that have already been de-risked. I'd also point out that there's really good opportunities to start by building circular economy facilities, waste recycling at small scale that use exactly the same equipment, exactly the same chemistry, exactly the same engineering. And my proposal has been to a couple of companies, as example, let's reprocess anode slime. Right? You got refineries, some of the big guys like BHP has a refinery, it produces anode slime. What if we set up a facility that recycles anode slime using those existing steps that makes money? And then 3 months a year, you campaign concentrate through it instead of anode slime. You fire up the electrowinning cell for those 3 months. And for 3 months a year, you treat it as a demo plant for minerals projects and not waste time or money on a demo plant. So that's another avenue. And then I may be premature in talking about this, particularly given there's a camera looking right at me, but I very much expect in the near future that Loop will be taking on a new managing director and that we'll be introducing a third avenue to our go-to-market strategy, which is raising some money, acquiring an asset and developing it our damn selves. So we are very fortunate to have been hosted by the Macquarie University Deep Tech Incubator. We get an amazing amount of wonderful support, and I want to go on record pointing right down the camera and say thank you, Macquarie Deep Tech Incubator. We have an amazing lab. We will be conducting a pilot cell operation in the near future at our lab. The intent would be then to do our demonstration in the field at a mine site.
Thanks for the talk. It was really great. I just have two quick questions. So it's how fascinating that you can, recover more than 99% of chalcopyrite, which is usually called refractory because of the passivation issues. So first question is there any particular reason that you choose the cupric cuprous redox couples rather than ferric ferrous? And the second question is, was passivations and issues in terms of chalcopyrite leaching in your study?
I'll start with the second question first. No. I've never encountered passivation issues. I remember, because I worked for Intech back in the day. I started my career with Intech, and there was a concern early in the piece, would gold be passivated? Not the chalcopyrite, but would gold be passivated? And we were able to disprove, no, it was not. Gold was also not passivated. Coming back to your first question. Oh, age is a terrible thing, isn't it? Tell me, what was your first question again? Oh, cupric cuprous. Yeah, the cupric cuprous couple is more robust than the ferric ferrous couple. It's much less pH dependent. So iron, you only have to sneeze and iron will come out of solution, and then you bugger up your couple, whereas copper 2 stays in solution until pH 3.5 or 3.3, and copper 1 stays in solution until pH 7. So you've got really robust pH chemistry to work with. It does the same job.
We'll take a last question then.
Thanks, David. Look, what happens to the sulfur? The sulfur mysteriously.
Well, 95% of your sulfur stays as elemental sulfur and goes out with the residue with the hematite. And as I said, it is possible, should you wish to do so, to recover that sulfur and sell it if you want to.
Yeah,
And if you've got selenium and tellurium, they will go with the sulfur. So you would recover it from that sulfur phase.
Okay. Another one. When do you think the pilot plant would be available?
All going well, it will be up and running and stable by Christmas.
Okay. Okay. That's good.
Join me in thanking David once again. Dave. So thank you all for coming. Next week we have Felix Quach from Plot Logic. He's going to talk to us about mine imaging scanners, enabling precision mining, and we hope to see you all next week in person. Thanks.